Okay, so we are recording. Welcome to Math219. Let's see here. Real quick, I do want to point out that we are recording here. And so very likely your voice is not going to be picked up by the microphone, but it does have a little bit of a radius on it. And so especially those of you in the front, it's possible that if you say something, your voices might be picked up. So you've been warned. So diving in, y'all have seen this before. I'm not going to go through all this stuff again. That was kind of the whole point of having a recording, right? So I wouldn't have to do it all on the first day of class and eat up a whole lecture. So what I want to do is just come down and emphasize the most important thing, right? This is a course about ideas, right? So this, I know so many math classes are, here's the formula. Make sure to know the formula. Here are various algorithms that you need to be able to, execute, right? And so you go and you memorize formulas and you rehearse algorithms. And on the test, you regurgitate formulas and you perform the algorithm. So that's just not what this course is about, and that approach won't work in this course. There's too much going on. Right, the way that we're going to apply ideas is just not mechanical, right? So the only realistic way forward in this class is to actually understand the ideas to the extent that you can see how they apply in different circumstances. That's the goal. That's what will allow you to do well in this course. And of course, I said a bunch more stuff about that and other things in this recording that y'all have already watched. So enough of that. We're going to move on now to the introduction. Reminder, all of these notes that I'm going to be putting up on the screen are available on the class website, right? And if you click on, I think it's course materials or something like that, specifically the website I've created for just our sections, right? Then all of these notes are in there. So I encourage you to download those or, get them onto whichever device you plan to be taking notes on in class or however you're going to do that. So here we go. The big question, why are we here? Right, why are you taking a course in multivariable calculus? Now, I do know that for many of you the answer is because my major requires that I take a course in multivariable calculus. So next question. Why does your major require that you take a course in multivariable calculus? I'm going to start with what I hope you've already bought, namely that single variable calculus is important. Y'all have taken at least a year of single variable calculus. You've seen a bazillion applications of single variable calculus, right? There's basically two kinds of questions that you deal with in single variable calculus. This is an overstatement, oversimplification, of course. But questions about how things change, the process of stuff changing, right? Which is a huge, unbelievably broad category of questions, and that's what derivatives describe, right? So derivatives are the tool that we use to understand stuff changing, right? So that's natural. Integrals. How do integrals show up in applications? And it's what I like to call accumulating quantities. An accumulating quantity, that's a term that I find convenient. It is something where the whole is the sum of the parts. Right? So various examples of this, if you have a lump of clay, let's say, right? The mass of that whole lump of clay is the sum of the masses of the parts if you were to slice it up, right? Ditto a loaf of bread. The mass of the whole loaf of bread is the sum of the masses of the slices of the loaf of bread. Right? So the whole is the sum of the parts. Another example, area under a curve, right? What a lot of students think of as being why we care about integrals is because it allows us to compute the area under a curve. Side note, not really. Comes up now and then, I suppose, but most of the time, that's not why we care about integrals. We care about integrals because they allow us to compute all these other accumulating quantities. Okay. All right, so anyway, hopefully already you're believers because of derivatives and integrals and the bazillions of applications you've seen of those, that single variable calculus is important. All right. Now, by the way, I something about the way I teach, I tend to, get going. I build up a head of steam and talking and making points, and then I forget to pause and give you all a chance to fit a word in edgewise. So does anybody have any questions so far? I have to make this conscious effort to stop and solicit questions. Everybody's okay? All right. Okay. So, single variable calculus is great, but the world is not one-dimensional. The world is three-dimensional, at least as we understand it. Right? So, three-dimensional world, single variable calculus being intrinsically one-dimensional, there's the disconnect. So here are some examples of stuff changing and the whole being the sum of the parts that are more complicated, and that single variable calculus isn't really very well set up to deal with. So for example, let's suppose you are in a three-dimensional context, right, which we live most of our lives in a three-dimensional context. And let's suppose here's me, right, and I'm moving with some velocity. Maybe I'm on a plane, right? And I'm moving in the x direction to some degree, but also to some extent in the y direction. I'm also kind of going up somewhat, so some angle, whatever. And as I move like so, I ask the question, how fast is temperature changing? Now, temperature may be given as a function of position. And my position is changing, though, and I'm moving, again, with the kind of components in all three different directions. How do I deal with that, right? How do we put it all together, and as I fly through space, how fast is temperature changing with respect to time? So this is not intrinsically a single variable calculus problem, right? This is unavoidably a multivariable calculus problem. We have three different parameters, x, y, and z, and all of them are changing. So multivariable calculus is going to be our tool to answer a question like that. Here's another example. Y'all have seen the one-dimensional version of this. The one-dimensional version is where you have a one-dimensional, let's say a rod of varying density, some kind of a metal that's got more sort of iron on this side, and it's got more sort of aluminum in the alloy on this side, and so the density is just varying. Well, all together, this rod of that length, how much mass is there in it? And y'all have seen, I presume, in your Calc 1, Calc 2 classes, you chop that up into little pieces, and on each little piece, you add it up. And well, here's the problem. Suppose you have a three-dimensional lump where density depends on x, y, and z. Now, how are you going to compute the total mass? And you can't just multiply density times volume. But furthermore, you also can't just slice it into little pieces, into little, thin kind of, little coin-shaped, short little cylinders, and talk about the density on those either, because the density depends on all the variables, including z. So now the single variable calculus, do an integral approach fails. So what do? How do we compute this mass? Right? This too is an unavoidably multivariable calculus problem. So both of these questions, and we've seen single variable versions of all of these. Single variable calculus, though, won't cut it with these more general versions. Is everybody with me? Okay. Now, some students find these examples unpersuasive because, after all, if you need to know how fast temperature is changing with respect to time, you could probably deal with that with a thermometer and a stopwatch, right? And then, what's the mass of this thing? I don't really need to. Do I need to bring calculus into this? Why don't I just set it on a scale, right? So perhaps unpersuasive. So these are, of course, easy kind of starter examples. I want y'all to see this sort of the foot in the door of where we're going. But now let me show you some harder questions where there is no sort of easy out. Okay? And I like to show examples in several different fields of study. We're going to start with economics, largely because a lot of people don't realize that there's lots of applications of math in economics. So here is an example of what an economic model looks like. Now, I made up this equation. It doesn't have any actual bearing on economics. That's not the point. The point is this is the kind of thing that an economic model might look like. You have several different quantities, right? And these quantities, price, quantity, different use of the word quantity, interest rate, capital, labor, these different parameters are involved in some scenario, some real-world economic scenario, and I can't particularly write any one of them as a function of the others, but I can sometimes say, look, they have to combine, because, efficiency has to be maximized, or because, some point of view about economics, I might be able to write down some equation that has to be constant. For example, something like this. So a lot of economic models end up looking kind of something like this. Okay, so that being the case, in this situation, how would I compute dp dt? Well, hard problem, right? Because if you look at p, the thing whose derivative I need to compute, here it is, there's p. Can I just solve for p? No, not even close, right? Look at that. It's cubic, but even worse, it's involved in an exponential. You cannot analytically solve for p. How can you take the derivative of something if you can't even find it, right? So it turns out, this is going to be something we're going to talk about in about a month, if I remember correctly, that there is a really clever multivariable calculus idea that allow us to do this. And it is tricky, and it's sophisticated, and it is nevertheless something that will allow us to take a derivative of p without ever finding p in the first place. Okay, so this is called the implicit function theorem and implicit differentiation. Some of y'all may have seen or heard versions of this previously. Okay, how are we doing? Everybody on board? All right. I like to point out at a time like this that a lot of people seem to think that there's no use for math above 3 dimensions, because after all, we only live in 3 dimensions, and what are we going to try to prepare for the possibility that we'll be transported like in a science fiction movie into a 4-dimensional world, or we're going to do some time traveling or something like that? No, absolutely not. Look how boring of an example already demonstrates why we need more than 3 dimensions, and it's because variables are not all coordinates, right? X, Y, Z, we're now out of position coordinates. There's only 3 position coordinates. These aren't position coordinates, right? So we find ourselves doing what I'm going to call 6-dimensional math here, because don't forget about time, right? Time itself is also one of the variables involved in the calculation. And so we're doing 6-dimensional math, just trying to do a little econ. It's not like crazy advanced particle physics or anything weird like that. So please don't buy into the common nonsense, in my opinion, that you don't ever need more than 3 dimensions, right? And clearly, sometimes you do, and it's not even that weird. Is everybody good? Okay. Now, good news for y'all. You're never going to have to visualize or certainly draw anything beyond 3 dimensions, because, of course, right? You can't. I mean, I can't. Nobody can. There were rumors about this one mathematician. He was so good at theorems of math that involved 4-dimensional space that some people suspected maybe he's a 4-dimensional alien and he can see through 4 dimensions or something. But nonsense. He was just really good. Okay, how everybody's comfortable? Okay. All right. Here's a bunch of multivariable calculus. Anyone in here who is studying physics or engineering? you're gonna see all of this business here. This is called Maxwell's equations, and it's very scary to look at. Don't worry about it. We have all semester to figure out how all this stuff works. So first question, we need to understand what these things mean. What is that right there? It looks kind of like an integral symbol, but there's three of them. Why are we integrating 3 times? What's going on there? Right? Then there's, what is that? That looks like a differential, but it seems to be a vector. That's strange. What's going on there? We need to figure out what that means. What is that symbol? Sure. There's a lot of stuff we need to know what those things mean. Fine. That's not all. We also need to know what's the best way to understand these statements. So that statement there and this statement here, it's one thing to understand the pieces that go into the statement, but what is it saying, right? What's the best way to understand each of these meanings? And by the way, how do they relate to each other? It turns out, again, we're going to see this way down the road. Turns out that these two statements are extremely closely connected to each other. And again, that's going to take us a while to get to. And then lastly, we're going to be talking about what do these statements, once we understand the meanings of these statements, what do they actually tell us then about, for example, electric fields? So these top 2 statements here are actually making very powerful statements about how electric fields work. And that's going to be something that we're going to be moving towards. So multivariable calculus is going to be the answer to all of these questions. Right? So part of the answer to the question, why do we need to understand multivariable calculus? Well, it's so that we can understand what this is saying, and so we can understand points of view on what this is saying about various objects, including the electric field, and likewise magnetic fields and various other gravitational fields, other things. Okay, everybody okay? All right, again, this is the very end of the semester stuff. All right, and here's another example. Anybody's going to be a chemistry major. One thing you're going to need to understand as a chemistry major is how do molecular bonds work. Now, y'all will eventually take a course, I think, chemistry majors will take a course called physical chemistry, which is basically, well, it's a lot of things, but among the topics covered, they typically do a little intro to quantum mechanics. And here's the thing, molecular bonds, they come from the behavior of electrons. Well, how do electrons actually behave? I hope y'all didn't actually believe what they told you in middle school about electrons being teeny tiny little baseballs that go around in circular orbits, kind of like planets. That was all nonsense. That's not true, right? I was surprised to find this when I was your age or so. Electrons obey Schrodinger's equation, and it's complicated. And it's partial differential equations. So y'all will start to have the tools to address this kind of thing after y'all take Math 353 or 356, or better 453 or 551. But anyway, we're not going to do any of that in this course, obviously. But nevertheless, this is multivariable calculus. Doesn't really quite look like it, but it is. This is certainly multivariable calculus. And case could be made that these functions themselves are actually these are actually pretty complicated objects themselves, and they're kind of multivariable objects of their own. So again, if you're a chemistry major, what we're going to talk about with multivariable calculus, critical to being able to make sense out of the fundamentals of how chemistry works. What do you think? Okay. All right. So. Now, these were just 3 that occurred to me, top of my head, right, while I was writing these notes out. There's countless more applications. And I like this little sort of concluding sentence here that I think is supported by all the previous examples, and that multivariable calculus, it's the calculus of the real world, right? Single variable calculus is nice when everything lines up and it's straight in one direction and constant in the other directions, and when everything is convenient, single variable calculus can work. But when things are not convenient, when things don't just line up perfectly, you need multivariable calculus. When you're living in a three-dimensional world, a multivariable world, you need multivariable calculus. Okay. Pausing again. Is everybody happy? All right. So, moving along. Chapter 1. Linear algebra, prerequisite for this course. I hope everybody's had either Math219 or Math221. Oh, okay, right.
Sorry, I'm looking in the right class.
That's all right, yeah. I should have told her 235 down there. She's probably looking for Mike Reed's class. So linear algebra, prerequisite for this course. This book does topics in an order that's a little different than I would have. They don't get around to sort of reviewing the linear algebra until section 1.6. So I want to start with that because just to get it behind us. So hopefully y'all remember all your linear algebra. I'm going to hit some highlights, but by and large I'm going to expect and assume that y'all are comfortable, proficient with all your linear algebra stuff. Now, when I say all, there's a lot that y'all saw in linear algebra that we're not going to touch at all in this class, and don't worry about it. So, for example, Jordan canonical form, that's not going to come up at all, not even a little bit. Eigenvalues, eigenvectors, I don't think those are going to come. Well, there's one place where maybe they come up just tiny, a little bit. Mostly not. But basics, what I'm going to call basics, I do expect that you'll be good at and remember. So real quick, now this is mentioned in section 1.6, but since it's not covered necessarily in all linear algebra courses, it's pretty geometric. I don't think this gets used much in a linear algebra course other than to be mentioned. So since you might not have seen it, here it is. There's not that much going on with this statement. It's what I consider to be pretty believable. When you add vectors, this being the sum of two vectors, that side of a triangle is always no longer than the lengths of the other two sides. Right, so this is a nice sort of interpretation of this inequality, is that green plus blue is always greater than or equal to orange. And again, at a glance, geometrically, it's extremely believable. Y'all have heard this statement, the shortest distance between 2 points is a straight line. Well, there you go. This orange distance is the straight line connecting these 2 points, and so that's the shortest distance, right? Not much to say, really. Pretty geometrically satisfying. Everybody buy it? All right. Cool. All right, now here's one I'm sure you've seen, but you might not have seen it this way, and that is how to multiply a matrix times a vector. Again, I know you've seen that before. Importantly, though, a matrix times a vector, matrix-vector product, can be computed different ways. Now, what y'all may have seen is that when you have your matrix here, right, and your vector here, then you kind of do dot products. One row at a time, dotting with the column vector, and those dot products give you the coordinates of your product vector. Fine, that's true. That will get you an answer. It's useful in other ways as well. And I don't have anything against that point of view, but it is not good enough on its own. There are other points of view about matrix vector multiplication. This one allows you to make certain connections that you can't make with that dot product point of view. So in particular, just make sure that you're comfortable with how a matrix vector product is a linear combination. Right, there it is. It's a linear combination. It's a linear combination of, well, let's see here, apparently these columns of the matrix that you're multiplying a vector by. Matrix vector product is a linear combination of columns. And specifically, it is the linear combination that uses the coordinates of the vector as the coefficients. Right? So now I'm curious how many people saw this in their linear algebra class. No, not very many. Okay. Well, few. Okay. All right. Okay. So some of you may not have seen this before. This is extremely useful. Again, different points of view on things are useful in different situations. And there are some situations where this is just invaluable. You've got to have it. Okay. So, make sure you're comfortable with this. Questions? Oh, let me point out, I made this observation very first thing today that, we're not interested in answers, right? We're interested in ideas and how ideas connect to each other and relationships and stuff like that. This is a pretty good example of that. So computationally, again, if what you're interested in is the number at the bottom of the page, I wouldn't even recommend using this formula. If you just have an actual matrix of numbers given to you and a column vector of numbers given to you, and your only goal is to get that result, the numerical result, then use the dot product formula. Absolutely. It's by far the easiest one. Yeah, for sure. Right? That's just not what mathematicians do, though. Right? No one has come into my office in 20 years and said, hey, here's a matrix and here's a vector. Multiply this out for me. It just doesn't happen. Right? What we need, and what comes up a lot, is to understand how different things relate to each other. So what we've got here is we've got this operation called matrix vector multiplication. Now here is a completely different algebraic concept, the idea of a linear combination. We've got a matrix, which I can think of as an object of a sort, but I can also break it down and look at its columns. Those columns are themselves vectors, right? And likewise, I can think of this as a vector, but I can also think of it as a list of coordinates. So all of these different things relate by way of this point of view on matrix vector multiplication. The point here is not the computational tool. The point is the relationship between the objects. Does that make sense? All righty. Okay, linearity. Now again, I know you all have seen linearity. Just want to make sure everybody's comfortable with it. We're only going to talk about what I like to call Euclidean functions, namely the domain is Rn, what I casually like to call Euclidean space. And the target also Euclidean space, not necessarily the same dimension. So note N and M there don't have to be the same. So anyway, Euclidean only, and that said, a function is linear if it satisfies this condition. Right here. Hope that looks familiar to everybody. Real quick reminder, my favorite point of view anyway on how to think about this is that if you have a linear combination, namely a sum of scalar multiples, that you put into a function, you can just as well do that same linear combination, namely sum of scalar multiples, to what comes out of the function. So, said differently, you can do the linear combination before you plug into a function or after you plug into the function, and linearity means that you get the same thing either way. So, anyway, it's one point of view. Okay, I'm sure y'all have seen that and done various things with it. You may recall, for example, that these two formulations are equivalent, and likewise, these two formulations are equivalent. So sometimes this top one is the most convenient one to work with. There are other times when 2 or 3 might be more convenient to work with. So it's a good idea to make sure that you're comfortable with all three of these. And by the way, another good exercise, make sure you're comfortable with how to show that 1 and 2 are truly equivalent. And likewise, how to show that 2 and 3 are equivalent. So this is, I'm going to call this an informal, exercise, something for y'all to take a little time, do on your own. Make sure you're comfortable with that. You're not going to turn it in, but I do a lot of this kind of thing. Certain facts that I think students should be good with, but we just don't have class time to review old stuff from previous classes. So take a few minutes on your own. Pausing again. Questions? By the way, that reminds me of another thing I wanted to mention. Something really unfortunate about this class in that we just have so much material that has to get covered. It's tremendous. This class is more full than any class I've ever taught. It's just packed with material. So I have to make tough choices as to how am I going to spend class time. Right? What makes the cut? What rises to the level of something that's worth us, actually talking about in class? And I have to have there. These things have to be there. What material is it that I'm going to leave for y'all to read in the book after y'all can read certain things and digest, and they don't really necessitate class time. So I hate having to make these choices. I would love to be able to say everything about every subject that we're going to cover in this course. The minutes just aren't there. Anyway, so this kind of thing where I'm going to wave at certain things for y'all to look at on your own, that's going to happen from time. Well, it's going to happen a fair amount, actually. Okay. All right. Oh, and of course, some of it I won't even wave at anything that's in the book that's not in the excluded material section of the content syllabus. It's all stuff that you should at least have looked at, and just keep in mind it's all fair game. You're responsible for all of it, and really all you can count on is that anything that I feel like deserves being discussed in class, I will discuss in class. Everything else is what it is. All right. Okay, so linearity, a quick few examples. Y'all have heard the term linear transformation. Again, transformation is just fancy talk for a function. So a linear transformation is just a function that's linear. So a couple of examples. If you have a fixed vector, A, not allowed to change, just totally fixed, you can use that to define a function that I'm going to call P here. P is the act of dot product. Oh, I shouldn't have done that. The act of dot producting, right? Some given vector x with your fixed constant vector A. And this function P is linear. Now, this is easy to prove. Again, you can do it on your own. Good little practice exercise to make sure you can prove that dot products are linear in this sense. That is, I should say, a function defined by this formula is linear. And this motivates that language that I just corrected myself for using seconds too early. It's awkward to go around saying dot product can be used along with a fixed given vector A to define a function P, which is linear. That's just a lot of words, right? And it takes up it's time and inconvenience. And so we just casually say dot product is linear, just because it's easier to say. But when people say dot product is linear, this is what they mean. Everybody okay with that? Cool. Likewise, cross product is linear. In the same sense, in the sense that you can use a given fixed vector A to define a function C, which simply cross products with your given fixed vector A, and that function is linear. Okay. Now here's one that weirds students out sometimes, and that is something similar you can say about determinant. Determinant, in a way, set up according to certain details. Determinant has an aspect of linearity about it, as follows. If you fix most of the rows of a matrix, not allowed to change. And if you then say, all right, well, look, at this point, any vector that you give me, any single vector that you give me, I can make that the last row, and thus, with that given vector, I can then talk about the act of taking the determinant of the overall resulting matrix. Right? So again, the first n minus 1 rows are fixed, not allowed to change. That's just set. You give me a vector x that completes a matrix. Once I have a matrix, I can talk about the determinant of that matrix. Altogether, this action of taking the determinant of this matrix that you get by appending an input row x, that function is linear. So again, I expect a lot of you might not have seen this before, but it's a pretty cool fact about determinant. As I've got it stated here, I'm applying this to where you take your input vector x and you make it the last row. You don't have to make it the last row. You can fix all but the third row. Make your input vector that third row, that gives you a matrix, take the determinant. That function also linear. It works for every row. It also, weirdly, works for every column. So determinant has all these different multiple linearities about it in these different ways. And so in general, this property is called multilinearity of determinant. Anybody seen this before? I'm just curious in Math221 or Math218, either one? No? Okay. I think anyway, let me stay off of my digression, but I think this is a really important fact about determinants and really useful in a lot of ways. All right. Okay, let's see here. Where's the button? Here we go. All right. Okay, moving along. Here's a nice fact. Let's see, by the way, let me look at the clock. I have until, is it 2:30? Okay, right, 12 minutes. Okay, roughly speaking, linear transformations can always be represented by matrices. It's a really neat fact. Now, in order to be careful, let me fill in the blanks of details. I'm very importantly, only going to be talking about Euclidean linear transformations here, so it's just the category of Euclidean linear transformations. And when I say a linear transformation is represented by a matrix, what I mean is, given a matrix, this right here, this is the function that I mean when I say, make a function out of a matrix. So given those specifics, every linear transformation is a matrix. Every matrix is a linear transformation. Key fact. Okay, so now again, here's an exercise. If you want to know why is it that every matrix is a linear transformation, that's a plug and chug. You can just take the formula here, take your matrix, make a function out of it, take that formula, plug it straight into the definition of linearity, and just confirm that sure enough, it works. And matrix algebra, laws that you know about matrix algebra, will allow you to do that. Okay, so good exercise. Oh, another thing I wanted to mention. When I give you these unofficial, suggested exercises, if you don't know how to do them, or if you're not sure how to get started, or if you get kind of halfway through it but you reach a dead end and you're not sure where to go from there, come to my office hours. I'll be very happy to help you with these things. Right? So my goal when I say that this is an exercise that y'all should do on your own, I don't mean literally that you shouldn't get any help on it. I just want y'all to, you make sure you're good with it, and if you are, great. But if you're not, come talk to me. Happy to help. While we're on the topic of office hours, let me remind you, Professor Hughes and I are doing a reciprocal agreement. So his students are welcome at my office hours. My students, y'all, are welcome in his office hours. So that doubles your office hours options. Oh, and I just posted a couple of hours ago our TA office hours, which are going to be, I think it's Monday and Wednesday evening. I don't remember which hours, but in the evenings on Mondays and Wednesdays, and I think there's some Saturday hours. Anyway, check the website. You might find those useful as well. Okay, here we go. Another thing I want to point out, this symbol right here, maybe y'all have seen this before, but it's a mathematician's shorthand for there exists, or there is, something along those lines. Certain phrases mathematicians find themselves writing down over and over and over again, and it gets a little tiresome, and so we invent little shorthand notations like this. All right, is everybody good? Okay, so moving along, let's talk about how to prove this the other way, though, and this is where it gets tricky. How do I show if I have a linear transformation? Somebody's come to me with a linear transformation. I know it's linear. How do I know that there's some matrix that reproduces that function in this way? How do I know that matrix exists? And even if I know it exists, how could I find that matrix? Kind of a hard question if you think about it. So the way we're going to prove that, it's a little bit of algebra and a very clever choice. Here we go. I'm going to start by reminding you that if you have a vector, I hope you all have seen this before, but every vector is a linear combination of standard basis vectors. Reminder, these standard basis vectors, like this thing here, is a 1 in the first position and then all zeros after that. This thing here is a 1 in the last position, as indicated by the subscript in here, and then all zeros everywhere else. And if you just take this expression where you use your coordinates as coefficients in a linear combination of standard basis vectors, you get the original vector back. It's a nice, you just got to write it down and kind of multiply it out, and sure enough, it works. Neat observation, though. I hope y'all have seen this before. Flashbacks to your linear algebra class. When you do a change of basis, right? You write a vector with respect to a basis. Y'all remember change of basis from linear algebra? Maybe? So anyway, the coordinates of a vector with respect to a basis are defined. Really kind of the definition of coordinates is that they are coefficients in the appropriate linear combination. Call back. Okay, so we're going to take this fact, here, which you'll notice here, I've just plugged it in. T of x, then, is T of this linear combination, and then here's where I cite linearity. Linearity says that if I have a linear combination on the inside, I can rewrite that as a linear combination on the outside. Everybody good? Okay. All right. So here's where here's the clever choice, the thing that makes it all work. Arbitrarily. So I'm pulling this out of nowhere. Right? I'm going to choose to take these things here, the images of the standard basis vectors, By the way, the word image means what comes out of the function when you plug something into it. So t of E1, that's the image of E1. So in general, these things I have circled in orange are the images of the standard basis vectors. Let's make those the columns of our matrix. Now that's a choice. I'm creating a matrix here. I choose to create the matrix like so. And having done that, let me try to fit all this onto the screen. Here we go. Having done that, let's see. T of x, which we previously saw was this, namely this. Well, each one of those, T of E whatever, is just a column, a sub whatever. Plug that in. And we win. It just automatically works because what you see here, here I have literally a linear combination of columns, and 2 pages back, that is one of our alternative definitions of how matrix multiplication works. And so T of x equals AX, and I've got a matrix that describes my linear transformation. Everybody good? I hope you might have seen this in a linear algebra class. I think this is really, really important. There's different ways that you can think about this. One way to think about this is that there is this one little clever choice that proves that this matrix exists. Here's a different way to think about it. If you find yourself with a linear transformation, some linear transformation, maybe you don't even have a formula for it. Maybe all you know about it is, well, one of my favorite examples, a rotation. Right? So you're going to rotate around the origin by a certain angle. Right? Well, immediately I don't have a formula for how you rotate around the origin by a certain angle. How would I come up with a formula for that? Well, I know it's a linear transformation, and linear transformations are represented by matrices, and here's my magic formula for how to find the columns. All I have to do, apparently, is look at the standard basis vectors, rotate those. I don't have to do it for every vector. Do it just for the standard basis vectors. Make those the columns of your matrix. Bam, there's your matrix. That's your formula for your linear transformation. It's a crazy powerful little trick. Pausing. Everybody okay with that? Okay. All right. Let's see here. Last thing, and this would probably be a good place to end. Matrix multiplication. Now, real quick, I'm going to point out there are different ways to think about matrix multiplication, just like there's different ways to think about matrix vector products. You can think about matrix multiplication in terms of dot products, right? Row, dot, column, right? That gives you your product matrix one element at a time, and you can just compute all the individual elements. Very handy. And again, if arithmetic were our goal, then that would be all you'd need to know. But again, it's not. There are different ways to think about matrix multiplication. I encourage you to look these up, make sure you're comfortable with this, but matrix multiplication can also be thought about in terms of linear combinations of columns. And there's details involved in that, right? Make sure you're clear on all of those details for how matrix multiplication can be thought of in terms of columns. Now, side note, it can also be thought of in terms of linear combinations of rows with different details. That's another really useful way to think about matrix multiplication. Do y'all remember row operations in linear algebra? You can think of row operations as matrix products with what they called elementary matrices. Do y'all remember elementary matrices? That connection comes from thinking of matrix multiplication as linear combinations of rows. Right? So these other points of view, always useful in their different ways. What I want to make sure y'all are clear about here is that matrix multiplication, when each matrix can be thought of as representing a linear transformation, matrix multiplication corresponds to composing the two linear transformations. And it's very convenient that this happens to be the case. That this formula that you write down in terms of dot products of rows and columns, or take your preferred point of view, happens to correspond perfectly with composing the corresponding functions. Not obvious that this is true, but it is important that it's true, and it's very handy in a lot of situations. So anyway, I just want to make sure everybody's at least familiar with, comfortable with this fact. Is everybody good? Okay. All right. So we're going to draw the line right there, and we will pick up here on Wednesday with section 1.1. See y'all later. Have a good rest of your Monday.